As legend has it, about 2,500 years ago, a bunch of Greeks were in a boat out at sea when they threw a man overboard, drowning him. This man was named Hippasus, and his crime? Claiming that the square root of 2 was not rational. Why such an irrational response? Hippasus was Greek, and the ancient Greeks' understanding of number was slightly different than ours is today. Just like we do, the Greeks used natural numbers, meaning 1, 2, 3, and so on. And they believed that any other number could be represented as a ratio of two natural numbers. That is, they believed in rational numbers, more specifically, the positive rationals. But one simple geometric measurement posed a problem. What is the diagonal of a square? Say you start with a unit square, that is, a square with side length 1. The good old Pythagorean theorem says the diagonal length of this square is the square root of 2. What's the fraction for that? Hard to say. But the square root of 2 was surely the ratio of some yet-to-be-found natural numbers, they thought. But they thought wrong. This is, allegedly, where Hippasus came and stomped on their dreams. In this video, I'll show that the square root of 2 is irrational. That is, it cannot be expressed as the ratio of two whole numbers. The math we'll need for this is just basic algebra. At the same time, we'll look at how this argument is made, using a proof method called proof by contradiction. Here's the logic behind a proof by contradiction. Start with a premise. Say this premise is some fact you know to be true. Follow its logical implications and get to a conclusion. If the premise is true and the logical implications are valid, then the conclusion is sure to be true. But wait, what if we start with a premise whose truth value we don't know? Then we follow its logical implications and we find a conclusion that we know to be false. Oops. Now we work backwards. A false conclusion means our premise must have been false. To prove that root 2 is irrational, we'll use proof by contradiction. Assume the opposite, that root 2 is rational. Follow a watertight line of reasoning and come to a conclusion that contradicts our initial assumptions. This will show that root 2 must be irrational after all. Let's get started. Here's a statement that's the opposite of what we want to prove. The square root of 2 is rational. If root 2 is rational, that means that root 2 can be written as the ratio of two integers. Now a quick refresher on fractions. Every fraction has a simplest form. That means we can simplify 2/4 to 1/2, and we can simplify 20/15 to 4/3. Remember this notion because it will be important later on. So let's say a over b is the square root of 2 in its simplest form. Next, let's do some rearranging. Let's isolate the variable a and see what we can learn about it. So put on your working gloves. We're going to do some algebra. First, get rid of that ugly square root. So square both sides. 2 equals a over b squared. Distribute the power. 2 equals a squared over b squared. Multiply by b squared. Two times b squared equals a squared. Now stop. Good. You can take off your working gloves and put on your thinking cap. We've rearranged this equation in this particular order for one particular reason. Now do you see what we can say about the variable a? Pause if you want. We can now say that A is even. Here's how. We started by saying that both A and B are integers, so we know B is an integer. We also know that any integer squared is also an integer, so B squared is an integer. And since 2 times any integer is an even number, 2 times B squared is even. And if the left-hand side of the equation is even, then the right-hand side must be even too. Finally, any number whose square is an even number must be an even number itself. And if this last statement doesn't seem so obvious, consider these examples. Odd squared equals odd. Even squared equals even. Odd squared equals odd. Even squared equals even. And so on. For the sake of not getting too sidetracked, if you're curious as to why this is, I encourage you to pause the video, put on a second thinking cap, look at the factors of these numbers, and then jump back in when you're ready. Back to our equation. We know that A is even, so let's rewrite it as 2 times some integer, say 2x, since all even numbers are 2 times some integer. Now what can we say about B? Take off your thinking cap, put on your working gloves. We're going to isolate B. First, distribute the power. So we have 4x squared on the right-hand side. Divide both sides by 2. And stop. Put your cap back on and think. What does this tell us about B? Just like before, and by the very same reasoning that we used to say that A is even, this tells us that B is even as well. Here's how. X is an integer. We declared it to be an integer when we wrote 2x to stand in for an even number. That means x squared is an integer. So 2x squared is an even number. So B squared is an even number. So B is an even number. Okay, here's the contradiction. Look back at our original equation. We know a bit more than we did before. First, we discovered that A has to be even. Then we found that B had to be even too. But if we rewrite each of these even numbers as 2 times some integer, it becomes clear that this fraction is not in its simplest form. We started with the assumption that A over B is the square root of 2 in its simplest form. But we've just shown that it isn't. And with that contradiction, we have our proof. We wanted to prove that the square root of 2 is irrational. So we assumed that the square root of 2 is rational and took that to be our premise. Then, with working gloves and thinking caps, we followed the logical implications and found a contradiction. That A over B is in its simplest form and that A over B is not in its simplest form. The contradiction means our premise was wrong, proving that the square root of 2 is irrational. As Hippasus would certainly not have said, quod erat demonstrandum.